All right, it's 11:15. We'll get started. So any questions on the homework? Anything people want to talk about? Sorry, I had to cancel office hours yesterday, but I am available today and by email. So, if you have any questions, let me know. The first one, especially, you're going to want to look in the book for that equation, figure out what the plot is. And the hard part about the first problem is you need to figure out what the slope and intercept are and then what they mean for solving for those variables. So the first one will take you a little bit of work. And if you need a hint on that, let me know. Anything else people want to talk about? Okay, so we've talked a lot about polymers up to now in this semester, but we haven't talked a lot about how do you know what characteristics of the polymer are in terms of characterizing them either with experimental methods or thinking about how the theories that we've discussed and the concepts that we've discussed like molecular weight are connected to experiments that you would really do in the lab. And so a big part of at least material science and engineering is characterizing different sorts of materials. And so we're going to talk about some special techniques to characterize polymers, and we're going to connect those to the concepts that we've already learned. And so in this part, you'll learn about how some of the equipment works, or at least some of the theory for how the equipment works. We're not going to go into how to make a GPC, but you can use this sort of thing to help you figure out what the characteristics of whatever polymer you're interested in. So you have an osmometry problem on your homework. Let's see, we talked about SEC. We'll talk a lot about that today. Differential scanning calorimetry we'll talk about, because if you're interested in thermal transitions, that's one of the standard techniques. Every polymer lab has a DSC. Dilatometry is used in a lot of material science because people are really interested in the coefficient of thermal expansion for lots of different materials. We don't do dilatometry as much in polymers, but it's still useful if you're interested in the CTE of a polymer. We'll do a problem on N-group analysis. We talked a little bit about spectroscopy or frequency-based measurements. And so we won't do too much with that, but you can keep these things in your mind. And then in your advanced courses, you'll talk about light scattering and diffraction, XRD, small angle X-ray scattering. We also do light scattering in solution to figure out the molecular weight, and that's, like I said, in your advanced classes. Any questions on this or comments or things you want to talk about before we get into the slides? All right. So we're going to start with N-group analysis, and I think there's going to be a homework problem on this. But the idea is that if you know what the N-groups of the polymer are, or how many N-groups you have, you can figure out things like the molecular weight. You can figure out other characteristics of the polymer. And so this is really useful because, of course, if you have high molecular weight, a really long chain, you've got low concentration of N groups. And so if you have a signal from the N group and you can compare that to the signal from the backbone, you can get an idea of how many repeat units you have, or at least the number of repeat units per N group. And it turns out that the number of repeats per N group you can use to calculate the molecular weight, right? So if you have a bunch of smaller molecules, let me make those real stars here. And let's just say that all of these repeat units, so the number of moles of, say, styrene, is the same in these polymers versus this big polymer. And the big polymer only has 2 N groups, right? And the little polymers have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 N groups. So the ratio of the moles of N groups to moles of repeat unit tells you about the molecular weight. And that's something to think about because you're characterizing a volume of polymer. And so you can have the same volume of high molecular weight and low molecular weight. And in that volume, there will just be more N groups for the low molecular weight. So you can figure that out from N group analysis. So there are some requirements. You need to have a well-defined architecture, linear, branched, etc. But you need to know that. So you need to know that there's 3 N groups per molecule, or you need to know there's 2 N groups per molecule. Of course, a linear polymer is going to have 2 N groups, right? But you need to know that. You can't figure it out because you could have one giant molecule with a bunch of branches. And if you don't know it's branched, you're going to get the wrong answer. And you need a distinguishable N group. And this is usually done through titration or NMR. And so if you review your organic chemistry book, you know that you get different signals in proton NMR for different types of protons, right? I know you covered that. I know you love that part of organic chemistry, but NMR tells you about different protons and how they're arranged in the chemical structure. So if you have the right chemical structure, or if you do the right modification to the N group, you can figure that out in some sort of characterization, characterization analysis, and then you can calculate molecular weight. So we have to be able to measure the number of N groups. If you can't see the N groups, if you can't characterize them, you can't do N group analysis. We have to know how many N groups there are per molecule, or we need to know the molar mass. We need to know the Mn of the polymer, and we can figure out how many N groups there are, or at least how many N groups are functionalized. We can't have any sort of overlap of things in the repeat unit and things in the N group, or else we're not going to know what's going on. And we also need to have the N groups in sufficient concentration. So you can think about in a, let's say, 500,000 grams per mole polystyrene, how many moles of styrene do you have versus how many moles of N group do you have? And this is a key point because you can't do N group analysis if the molecular weight is too high. So think about this. Here's polystyrene that we know and love, right? If N is low, that gives us higher concentration of N groups, right? And if N is high, lots of repeat units, concentration of N groups decreases. It turns out that this is a key concept, thinking about how many N groups there are. Of course, we talk about it in terms of the analysis of the N groups, but it turns out that N groups can affect things like glass transition temperature, other things like that. We'll talk about that a little bit. So what's an N group on polystyrene? It's undefined in this structure, right? We don't know what's on each end of polystyrene. But when you synthesize polystyrene, or when you make a polymer, what types of polymers have we studied where you have a well-defined N group? You think back, all the stuff we've done, when did we specifically put a key molecule on the end of a chain and we know it's there? Go ahead. Initiator, right? Initiators are key molecules to put N groups on polymers, and you know it's there. What's the problem? Let's take free radical, right? We're doing free radical polymerization. What's the problem with just analyzing the N groups? What's the issue? Well, let's say everything's stable. Let's say everything's fine. But let's say we're doing a good job doing a good job with initiation. We know what's going on. What is the real issue in conventional free radical polymerization about N groups? If you compare combination versus disproportionation, right? In one case, combination, you're going to have an initiator fragment on each end of the chain. And then the other case, in disproportionation, you're only going to have an initiation fragment on one end of the chain. And so you really need to know how termination is done, whether it's done by combination or disproportionation, because you really need to know what the N groups are like compared to the molecules. So that's why in those problems, when we studied chain growth free radical polymerization, I gave you some hints about combination versus termination, and you had to tell me how many moles of molecules there were, or vice versa. I told you about which molecules had what N groups, and you need to figure out Q. Remember, everyone loves Q, right? And so you need to know that in order to do N group analysis. But my point is that there are synthetic methods to put specific molecules at the N group so you can do this analysis. And so we have an easy one with free radical initiation, but there are lots of other ones too. And sometimes you can initiate with one molecule and you can terminate with another, and then you just need to analyze both of those N groups and know that they're at the end of each chain. So it's really about knowing what the chemistry of the chain looks like, how the chain is started, how the chain is finished, or at least what the N groups are, and then you can do this type of analysis. And you'll learn a lot about that in your advanced classes. Any questions on that? Any comments? All right. If we're going to do free radical initiation of styrene, what's a common N group that we might have? Or what's a common initiator that we might use for free radical polymerization of styrene? You're really going to want to know that for the final. So we're gearing up. We only have a few weeks, 4 weeks left. And remember, the final is cumulative. And so it's totally fair game if I say, which one of these molecules is an initiator for free radical polymerization? Or please name an initiator for free radical polymerization. Go ahead.
Epoxides.
So epoxides are not initiators, they're monomers, right? They're 3-membered rings with an oxygen. Yeah.
Use benzoyl peroxide.
You can use benzoyl peroxide, right? It's a peroxide, so it breaks apart, makes free radicals to initiate. What's another common free radical initiator? Yeah. That's right. Yeah. So remember that. And, I sort of sprung that on you. You hadn't studied it, but it's that type of stuff. And along with Q, along with combination, disproportionation, you're going to want to know all those details for the final. So we will review some of the previous stuff to make sure we're all on the same page. And of course, a study guide will be published. You'll have an idea what's going to be on there, but don't forget some of the basics like AIBN and benzoyl peroxide. All right. So the point is, for N group analysis, you need to know what the chain looks like. So you know the ratio of N groups to the ratio of monomers, and you need to be able to detect the N groups. All right. So if we do some sort of titration, you've all done titrations, acid-base titrations, etc. There's a lot of different titrations, it turns out. And so this is an easy way to figure out if you have acidic or basic N groups, and that's the way that we'll think about this. And I'll give you an example problem today. Like I said, you'll have a problem on the homework as well, the upcoming homework. So really nice reactions for N group functionalization. If we have a polymer, this is polymer with OH N group. So this is some sort of alcohol or phenol group, and from organic chemistry that alcohol protons are a little bit hard to see in NMR, right? And so if we functionalize these alcohol N groups with something like bromoacetylation, and we put a bromine on there, it's really easy to see bromine by elemental analysis. This is now attached to the polymer chain. And if we have bromine right next to these two hydrogens, that's much easier to see in NMR as well, especially since we have this ester right here. And so those hydrogens are going to stick out in the NMR analysis because they're very unique compared to something like polyethylene oxide. There we go. You know, you've got these protons in PEO. Those are nominally equivalent because they have an oxygen on each side. And so making a nice NMR signature for these protons can be done with bromoacetylation. So there's a couple different ways to analyze those N groups. We're going to analyze it by bromine content in a second. If we take our OH functionalized polymer and we functionalize it with succinic anhydride, we get this group. What's this group called right here? Carboxylic acid. And so you can do an acid-base titration, right? Great. We can functionalize this OHN group with this thing called acetic anhydride. And so what acetic anhydride does is it puts a nice methyl group right here. Remember, the end of that line is CH3, not a hydrogen. I think you saw that thinking about one of those siloxanes in the practice exam last time. And so you can detect that by NMR. You can't titrate this methyl ester, but you do get this carboxylic acid that comes off. So if you do this correctly, you can back titrate this. And so you know exactly how many moles of acetic anhydride you use to functionalize the N group, and you can get an idea of what's going on at the end of the polymer. And this is your hint for the homework. Just that will help you next week. All right, so there's a couple different ways to make the N groups visible through synthesis or through post-functionalization. Of course, these only work when you have a polymer with an OH-N group, so you need to know that the OH is there in the first place before you do this functionalization. But you know, the conceptual part of this is more important than figuring out all the little details. But the homework problem or exam problems will look something like this. So I'm going to walk you through this. Yeah, you can get out your clickers. I do want to know who's here. We're still on CD. Evidently, this thing is not with it. Okay, so what this problem looks like is, you know, we'll generally say something like this. There's 1 gram of a sample of polyester polyol, and you don't necessarily need to know what that is, with an Mn of 3,000 grams per mole. Great. We treated it with bromoacetyl bromide. You don't need to memorize that. So I'll generally give you the reaction so you know that a bromine ends up at the end. So here's our polymer. Now we're going to put bromine at the end. The treated polymer was found to contain 4.88% by weight bromine when we do elemental analysis. That's for the whole polymer sample. Estimate the average number of hydroxyl groups on each molecule of the polyol. Okay, so we have this. So I'm going to walk you through this, and then we'll talk about what the answer is. And so for every OH group reacted, the molar mass increases by this amount. So we subtract 1 because we lose a proton, right? We lose this thing. And then we add this. So here's the bromine. There's the 2 carbons. there's the oxygen, and remember there's 2 hydrogens on there. So you should be able, rather than just staring at this PowerPoint slide, you should be able to figure out, okay, we started reacting with this bromoacetyl bromide, and from this reaction right here, we get rid of HBr. That's shown right here. And then you get this N group. So you need to account for the increase in molecular weight. So now we have an unknown, right? So let's make it X is the average number of OH groups per molecule that reacted with the bromine functionalized N group reagent. And so now we have a new molecular weight, which is 3,000, our original Mn. And then we're going to add number of N groups times how much the mass increases. Great. So the bromine content is 4.88% by weight. And so that's the number of moles of bromine over the new molecular weight. And so when we solve for X, we get X equals 1.98. So you can ring in, so I know you're here. And that is, 2. So if you see this problem, you're saying, okay, how many N groups does a polymer have? What are some reasonable answers? 2 is a reasonable answer, 3 or 4. You know, sometimes you get numbers less than 2, but for linear polymers, for a lot of the things we studied, you know, 2 is going to be in the ballpark. It's not going to be 100. It's not going to be 0.05. It's not going to be something like that. And so you're looking for something that's a low single digit integer. Now, it could be close to 1 because in some cases only one end of the polymer chain can be functionalized. But the point here is that 1.98 is a perfectly reasonable answer. Why is it not exactly 2? Does anyone have an idea? Because you don't always do perfect experiments, right? There's experimental error, there's uncertainty, you know, there's a lot of things that go into that. Maybe the molar mass isn't exactly 3,000 grams per mole. That's just a number I put in here. And so in characterization, all right, if everyone's rung in characterization, you need to take into account that you're not going to get exactly whole numbers of what you think you're going to get. There's going to be plus or minus some percentage. What's a good plus or minus percent for an experimental measurement? So if you could go and say, okay, you know, it's 3,000 grams per mole. What's a good experimental error if you've done everything correctly? Just ballpark, like using your engineering brain. Plus or minus 5%, plus or minus 10%. I mean, we say in the lab sometimes plus or minus 10% is fine. Of course, you want to do the measurement enough times and have enough replicates that you can do statistics on it, get some error bars, you know, do your statistical tests. But plus or minus 5 or 10% is no problem. And plus or minus 10% on 3,000 grams per mole means that you could have, 3,300 to 2,700 grams per mole. So that seems like a big span, but that's plus 10% and minus 10% from the nominal value. So don't be afraid when you see numbers like 1.98, you're like, oh, what does 1.98 N groups per polymer chain means? That is an average of the distribution, right? So that's just a little soliloquy on you're not going to get perfect numbers when you're dealing with characterization. Any questions or comments on that? All right, you'll be able to practice N group titrations. And so if that's not clear on the homework, we can talk about it next week, but it's based on this concept where you're comparing something in the polymer chain to something that's visible in the N group. All right, we're going to move on to size exclusion chromatography, and this is a really important concept that will serve you well in your future polymer career. And this is covered in detail in advanced polymer classes because this is so important. This is the gold standard for characterizing molecular weight of polymers. And so the point of size exclusion chromatography is that you're doing a separation, which is what chromatography means, separation based on size. That's why it's size exclusion chromatography rather than affinity chromatography or something else. So when are polymers big in solution? What are two things that go into like a nice expanded coil that's big? High molecular weight, and what's the other one? Good solvent, right? So high molecular weight polymers and good solvents, you get nice expanded coils. If you keep the polymer the same and keep the solvent the same, still a good solvent, and decrease the molecular weight, the coil gets smaller, right? And so we're talking about dissolved polymers. In good solvents. For the most part, but you'll know what the situation is. And we treat those like particles, but we're really talking about the size of the coil, just as we discussed in the conformation unit, right? So you have some tools to figure out what the size of polymer molecule is in solution. And you know that the size is going to be correlated to N. And of course, N is correlated to the molecular weight. So the tricky part about size exclusion chromatography is that big things come out first. Big things elute from column first. And so that's a really important concept. That is always true in size exclusion chromatography. And it's because the small coils get stuck in our porous media. So this is some sort of packed bed, silica, something like that, some sort of cross-linked gel even. And so they will elute more slowly. So here's time, or this is also called elution volume. Because the setup here, oh, let me make that an M. So the setup here is that you're putting solvent with dissolved polymer in the top, and then you're flowing that polymer and solvent down through this column. So you're moving solvent through this column. So as a function of time, you're getting more and more volume that comes out the bottom of the column. So time and elution volume, if you know what your flow rate is, you know how much volume you put through the column as a function of time. And so if you're detecting, so you have a detector right here, and you can measure a signal from the big particles and a signal from the small particles. You'll get a big particle signal at short time. And you'll get a small particle signal at longer times. This is not the best diagram if you've never seen what chromatography looks like and how you gather that signal. I'll try and get something better. We might have something better later on in the notes. But this is the most important concept for size exclusion chromatography. The high molecular weight comes out first. And I'll say that over and over and over again, and you will never get that wrong. All right. So the data generally doesn't have peaks like this unless you've made some polymer that's got two different populations of molecular weight. The data for size exclusion chromatography looks like this. Here's our elution volume, So this is higher volume or longer time. And this is amount of polymer on the y-axis that's dictated by a detector response. So the detector is basically measuring what's coming out of the column after things are separated. So this peak is separation by molar mass. High molar mass comes out first, then things with the molar mass a little bit less come out next. Then things with the molar mass a little bit less come out here, etc., etc. So you get a distribution of molar masses. What's a distribution of molar mass called in polymer science? What do we call that number? You're going to want to know this for the final. I guarantee it. MW over MN is what? Dispersity. And it turns out that this looks exactly like some of the stuff that we talked about in first moment and second moment of the molecular weight distribution. So you can get MN and MW, and of course dispersity from a plot that looks like this. Now the detector response is viscosity. Turns out there are viscosity detectors. So when the solvent gets a little bit more viscous, you know there's polymer in there. There's also refractive index. When you have pure solvent versus when you have a little bit of polymer in that solvent, the refractive index is different. So you can detect the presence of polymer that way. And there are some other types of detectors, but viscosity and refractive index are the two ways that you figure out how much polymer is in a given elution volume. Because remember, if you take a slice of this, that's basically a little volume that's come out of your chromatography column, right? Say 0.1 milliliters represents that little bit of integrated elution volume. And there's a certain molecular weight of polymer and a certain amount that comes out of there. So that's important to remember how this distribution is built up. So the magnitude of the detector response tells you how much polymer is in there or amount of polymer. And the elution volume gives you an indication of the molecular weight because it tells you about the size. So you want to think about how you put both of those things together to get this distribution. Now, it's the first time that you've seen something exactly that looks like this. And so we're going to pick apart this distribution and figure out what it means in future slides. Any questions so far? Does everyone sort of understand what we're doing with chromatography? So you're taking a mixture. Let me insert a slide here. Here's our column. And it's got holes in it. We have a detector to tell us how much polymer is in the solvent. And we have a mixture we put in a mixture of polymer chains in a good solvent. And what the column does is column separates chains by size, and that is an indication of molecular weight, as you'll see in a second. Okay, so you want to think about this, think about what we're doing, but we're basically separating all these chains and trying to figure out what the molecular weight is. And this is all based on the ability of us to equate the size of a molecule, because remember, size exclusion chromatography is only measuring size, with the molecular weight. So it really matters what this idea of the hydrodynamic volume is, or we need some idea to measure the size of the chain or get an idea of the end-to-end distance. So you can get out your clickers, right? I think we're up to 45. So we've got polystyrene of the same molar mass. So we have 3 samples of polystyrene, same molar mass in methanol, chloroform, and hexane. Which would you expect to have the largest hydrodynamic volume? So which pair, polystyrene and which solvent? So you got polystyrene here. We have methanol is here. Chloroform is here. And excuse me, and hexane is right here. And so we're asking for what's the largest size polystyrene coil in what solvent? I'll wait on this one. I think we're 45, so we'll get back to 45, 47 maybe. All right, that's looking pretty good. Oh, perfect. So what's the concept? If we're looking at solubility parameter, what's the concept that we're looking for? Good solubility, and things that have very similar solubility parameters are likely more soluble in each other. And so the polymer coil is going to be more expanded when you have a solubility parameter that is close to what the polymer is. And so you can pick that off and you can say that the smaller difference in solubility parameter, or the more similar the solubility parameters are, the more elongated the polymer chain is. And so that's really interesting. Now you can get qualitative comparisons between polymer size, looking at different solvents, etc. Okay. Now this is tricky to understand. And so hopefully you think about, okay, higher molecular weight polymers are big, they come out first. Lower molecular weight polymers are small, they come out last, there's a distribution. Okay, I sort of get that. That's the raw data. But this plot contains no information on molecular weight, right? It's only relative, high versus low. You need to do what's called a calibration in order to figure out the relationship between elution volume and molecular weight. And it just so happens that we usually plot this on log molecular weight on the y-axis versus elution volume on the x-axis. And this shows you that low molecular weight, or lower M, gives you higher elution, or volume. So what you do is you have something called monodispersed standards. And what these are is that these standards, I can get rid of this here. Standards have known M. It's set, it's on the bottle. This is a monodisperse polystyrene standard with Mn of 10,000 grams per mole. You buy that, you pay a lot of money for that. What's a technique? So you can't use a SEC to calibrate a standard. What's a technique to figure out what molecular weight of polymer is that's not SEC? What did we just talk about? N group analysis, right? NMR, N group analysis. A lot of work is done to make sure those standards are the molecular weight you think they are. So this could be a, let's say on this green line, this could be like a 50,000 gram per mole standard. This is like a 20,000 gram per mole standard, and this could be like a 5,000. Gram per mole. And so when you do SEC, you walk up to the big box in the lab, you ask the people who take care of the lab, what's your calibration standard and how long ago was this calibrated? Or I'm going to run a calibration standard before I run my measurement, because you really want to know how elution volume is correlated to the molecular weight. So this is what the SEC looks like. So it's the same idea, amount of polymer versus VE. Oh, VE is on there. But now you know exactly what the molecular weight of those peaks are because it says it on the bottle. It's the standard, or it's the calibration standard. And the key with lots of types of characterization equipment is it has to be calibrated. NMR is calibrated to TMS or some other type of very specific molecule. So SEC is calibrated to exact standards. Usually it's some similar polymer in the same solvent that you're using, because you want to make sure that the hydrodynamic volume doesn't change. Does anyone know how X-ray measurements are calibrated, at least wide angle X-ray diffraction? Yeah. So yeah, so sometimes it's ATP, sometimes it's silver BNA, but it's a crystal with an exact D spacing, and it's usually a single crystal or large grain crystal. So you know exactly what the X-ray spacing should be, and you can calibrate your detector that way. So that's a good one. Yeah, it's another calibration standard. There's lots of different ones. So anytime you do some type of characterization, say, how is this thing calibrated? That's a good question. All right, so we go from this amount of polymer to elution volume, and then we can, if it's calibrated, you can construct this log molecular weight versus elution volume. And now for any elution volume, well, let's stay within our standards. You can figure out, okay, that elution volume is likely that molecular weight. That elution volume is likely that molecular weight. And so you have an idea now what your elution volume versus molecular weight looks like. And you can put an unknown in there, and you're always measuring the elution volume, and so you can get the molecular weight from that. All right. Okay, that's great. So that's just talking about how we construct the distribution. And so this is worth looking at in terms of figuring out you have an amount of polymer in a small slice of elution volume, and you can get this information. All right, so we do some analysis, or we normalize it, and we can get our weight fraction versus molar mass. And from this, we can get MW, right? And you know, if you have weight fraction molar mass, you can likely get MN as well. And so this is how we start to construct MN, MW, and dispersity from this type of information. Okay, clicker question. So we have two different standards of polymer with the same chemical composition. Two standards. Okay, and so this is polymer 1. Oh, no, that's polymer 2, sorry. Polymer 2. And this is a different polymer with a different calibration curve. So two different calibration curves where now we've constructed the molecular weight versus solution volume curve. They have the same composition. So you could say these are both types of polystyrene if you want. Same solvent, same everything else. And the question is, which one is branched and which one is linear? That is tricky. And the way to think about this is if you have a linear polymer versus if you have a polymer that's branched, which one is more compact?
Right.
The branched is more compact, right? There's more monomers that are closer to each other in the branched example versus the linear, they're all spread out. And they could be exactly the same molecular weight, right? So you can have the same number of monomers in this molecule versus this molecule. And the branched will always be a little bit smaller because the monomers are closer to each other because they have to be because of those branch points. So the question is, which polymer is branched and which one's linear? So you can ring in. So the way to handle this, or at least the way I might handle this, is say, okay, they're the same molecular weight and the same composition. Which polymer comes out first in my elution volume? One comes out first. And do smaller things come out first or larger things come out first in SEC? Larger things come out first in SEC. And we just talked about linear chains being larger than branch chains for a given MN, because when we go horizontal here, we're keeping molecular weight exactly the same. And so now you can figure out which one is branched and which one is linear. All right, we are at 48. That's nice. And if you didn't ring in, here's the answer. 2 is branched and 1 is linear. And that is tricky. That's as tricky as these questions are going to get, because you need to think about the chain architecture. You need to think about what that means for molecular weight, and then you need to think about size. Oh, let me get rid of this. So in a good solvent, the linear polymer will have a larger hydrodynamic volume. And I promise you, I'm going to ask you questions about branched and linear, either on the upcoming exam or on the final. And branching will make the polymer more compact as compared to linear at the exact same molar mass. And so the linear polymer is going to come out faster. That is putting it all together, and that's hard. I could also ask you, this is exactly the same polymer. So not polymer 1 and polymer 2, but it's 2 different solvents. So I do SEC in one solvent, I do SEC in another solvent, and I get 2 different curves for elution volume. What solvent is better and what solvent is worse for that polymer? Or is the coil big or small? And you should be able to answer that, because of course the hydrodynamic volume is going to change depending on the quality of the solvent. So think about that in terms of polymer size, in terms of what the polymer coils are doing in solution for the specific situation. But this plot is really important for you to remember. And the key is, this is low VE, big, and this is high VE equals small. And the whole thing is which polymer chain is big and which polymer chain is small, and that depends on the situation. Any questions or comments on this? All right, don't forget your homework. I have some office hours. If you can't make office hours, shoot me an email. I'll see you on Monday.
Are your office hours today?